Hi, everyone. This is your lecture video for 11.7, which is titled Probabilities Involving AND as well as Conditional Probabilities. You should have found this worksheet on the classroom week agenda site. I have yet to come up with a good name for that, but if you don't have it and you'd like to follow along, you can email me and I will send you the link to that page, and therefore you can print it out from there or just have a clean copy. So with no further ado, suppose a bag contains 6 marbles and they're each lettered A, B, C, D, and F, so one of each, and we're going to draw one. Ultimately, we're going to draw 2 marbles out without replacement, okay? So first marble is drawn, and I'm sorry, with replacement, and then put back in the bag. Ooh, already messed this up. So the first example, we're just selecting a marble, putting it back in the bag. Then we're going to draw our second marble. What's the probability that we get letter A and then letter B? I don't know, just figured alphabetical order. How likely is it to get an A and then followed by B? So what's different here is the word and. In 11.6, we dealt with probabilities that included two or more events separated by or, but this is 2 events selecting an A, the other event would be selecting a B, and we're separated by the word and, okay? Hence the title of the section. So anytime I'm into some new territory, it's nice to fall back on just some fundamentals before giving you the formulas, at least right now. I think it's a little exciting to explore. So what I've done here is first kind of give myself a little visual of what it is we're doing. So here's our marbles in a bag. So we're going to draw one out, put one back in. Let me go back to a little more full screen here. And I'm actually going to create the sample space again because it's my first time dealing with the probability with the word and. So I know in my first pick I can get any one of those letters A, B, C, D, E, or F. And for my second pick, again, since the marble's going back in the bag, any one of those marbles is available. And what I'm starting to fill in now is the sample space. So all the green letters represent my first pick, and then all these second letters represent the second pick. So for instance, this top left corner, A in green, A in blue means first I pulled A, second I pulled A. Now in the position to the right of it, we have a green A and a blue B. That means I pulled A first and then B second. And that's actually what I'm looking for. I'm looking for pulling A first and then B second. And I believe that's the only place in this entire table where you're going to pull A first and B second. So I'm pretty much looking at the probability. I know there are a total of 36 possible outcomes here because there are 6 rows and 6 columns, of which one of them, getting A first followed by B second, is right there. One of those outcomes is successful. So to answer the question, the probability of pulling a marble first lettered A and then lettered B, as long as the marbles are replaced, is 1 out of 36. So what's interesting here is the probability of A and B just the sum of the probability of A plus the probability of B? And that's a common question. Do we just add these together? Question mark. So let's try it. We know we have to get 1 out of 36. So no, adding the probability of A plus adding the probability of B, right? Getting the probability of an A is 1 out of 6. Getting the probability of a B is 1 out of 6. 1 6 plus 1 6 is 2 6, which is 1/3, which is not 1 out of 36. So what we just seen here is that the probability events that contain the word and are not found by adding. What might we do? Well, I kind of gave a hint there too when we listed out the diagram. There were 6 rows, 6 columns for outcome. How did we find that denominator? How did we get the denominator of 36? We multiplied, very similar to the fundamental counting principle from earlier this semester. And then how might we get the 1 in the numerator? Well, there's one way to get an A, and there's one way to get a B. 1 times 1. So kind of spoiling it ahead here, but I have this written out. When you are calculating probabilities containing the word and, it's likely that you're going to be using multiplication, but it's not a guarantee. I'll get to that in a second. All right. Suppose a bag contains 6-lettered marbles, the same 6 marbles. Here we're drawing a marble and it's not going to be replaced. So I quickly ask myself, should this probability be greater, less than, or equal to the first? What do you think? Should this probability be greater than, less than, or equal to 1 out of 36? What's changed here? Well, what's changed is that there are no marbles being replaced. So is that going to sway it higher or lower? I have my guess. Did you? Do you have yours? So let's see. We'll see at the end. It's nice to kind of estimate your answer first. I'm just going to jump through a little bit here. I created the sample space again, especially because it's the first time, but I want to emphasize what's different here. It is going to be impossible to get the outcome A, then A, or B, then B, then C, or D, et cetera, et cetera. Why? Because if your first pick was A, it's not in the bag. It's not around for round 2. Right? So it's impossible to get A followed by A. And same argument for B. It's impossible to get a B, then followed by B. It's not in the bag if you pulled it out. So again, we're kind of thinking the fundamental counting principle here. I have 6, and I want to stress this, then 5. All right. Why times 5? Well, there were 6 at the beginning. There were 6 outcomes at the beginning. But once we chose one of them, now there's one less choice. Okay, so something happened, and now that's going to change the number of outcomes in the future. So 6 multiplied by 5. Again, this is really just a fundamental counting principle you've seen before. If you had that in your understanding, awesome. But I'm just kind of building up to what we're going to see in a formula in a moment here, right? So because something happened and it affects a future outcome, well, that's it. It's going to be one less. In this particular example, one less. So now we have 6 times 5, 30 total outcomes. And then I can quickly see in my sample space which where's the event of pulling an A then a B right there, 1 out of 30. So this is a little higher. This is more likely. And that makes sense, right? I hope you had that intuition from the beginning. You know, there's less marbles in the bag if you don't replace it. So, right? So I'm more likely to get B now because there's one less option to draw. So if I were to put back the marble A, there's a chance I can get A again. But if it's not there, it's less likely to happen. So this probability is closer to 1. This is more likely to happen. So with no further ado, the main ideas we've looked at so far are spelt out in boring math language here. No, I'm just kidding. 2 events are independent events if the occurrence of either of them has no effect on the probability of the other. So for instance, in our first example where we drew a marble out of a bag and then replaced it, listen, whatever I draw out, if I'm putting that marble back in the bag doesn't care when you reach in again. It doesn't move that marble to the left or the right of the bag. It doesn't put it any higher or lower in the bag. That's just silly, right? So when you replace marbles in a bag, typical probability question, that's an independent event. It does. What's going to happen next? Well, when you put the marble back in, it doesn't care. You have the same likelihood of happening. Or for instance, if you have a spinner from like Twister or just a game board of sorts, right? So some type of spinner and a coin. So if I spin the spinner with my left hand and I flip the coin with my right hand, those events are independent. What happens on the spinner has no effect on what's going to happen with the coin and vice versa. So it's silly, it's obnoxious to say, oh, if this is head, well, that now this wants to be red, right? It wants to be red. No, that makes no sense. So they're independent events. And when you have two independent events, their probabilities are found by multiplying each of the events' probabilities together. And if there are more than two independent events, the probability is just a string of multiplication. So that's all this sentence says. I think it's important here to understand what independent events are. They don't matter what the other one does in very layman's terms. Their probabilities are found by multiplying. And if there's more than two events, you're going to flip a coin, roll a die, and spin a spinner. You just find the probability of each and multiply them together. So now two events are dependent events, almost the opposite here, if one does play a role on another. So for instance, in the second marble example, B was more likely to be drawn. How come? Well, because we pulled out a marble and it was not replaced. So it played an influential role on what's going to happen next. This is called a dependent event, and their probabilities are found by multiplication. But if two events are, this should say dependent right here. I copied and pasted. So if A and B are dependent events, then the probability of A and B, you're still going to multiply, and we'll talk more about this through the lesson, but it's the probability of A multiplied by the probability of B given that A has occurred. So yeah, that's what does that mean? We'll do an example in a minute, but I just want to write it as that. So we're going to still multiply. We're going to multiply the probability of A, and then we're going to multiply by the probability of B given that A has happened. It's kind of a hard, there is a formula for it. For given a B as A has happened, we're not going to look at it. We're going to look at just easy cases in this course. So bear with me for a few minutes till we get to that example. But that's what we say the probability would be that A has happened. And there's a notation for that. The probability of event B, assuming that A has already occurred, is called a conditional probability of B given A. And it's written as P of B vertical bar A. We don't say that. We literally say B given A, that we read it as I just did. But just to describe it to you, it's P B probability of B vertical bar A. That's what that looks like. So let's do a few, at least a couple examples here. A coin is tossed and a die is rolled. Independent, automatically, right? At least you should be thinking that. I just mentioned that a few minutes ago. So what happens on a coin has no outcome on what happens on a die. And we want the probability of getting a tail, okay, and a number less than 5. So I want to get a 1, 2, 3, or 4 on this little number cube. So the above definition says if two events are independent, you just multiply their probabilities. The probabilities of getting a tail on a fair coin is 1/2. And the probability of getting a number less than 5 on a fair die is 1, 2, 3, 4. 4 out of 6. And that's it. And so this just multiplies to 4 out of 12. Simple enough to simplify this to 1/3. That's it. So the probability of two independent events, you just multiply their probabilities. And that was similar to the example of the marbles in a bag with replacement. So the probability of getting an A and a B, well, if you put the marble back in the bag, independent, doesn't matter. So the probability of getting an A, 1 out of 6. The probability of getting a B, 1 out of 6. Multiply those together, 1 out of 6 times 1 out of 6, 1 out of 36, as we saw. Two cards are randomly dealt from a standard 52 deck of cards. What is the probability that the first is a heart and the second is a diamond? Cute little picture there. We're dealing with a dependent event. How come? Well, we're going to select a card and then a second card. This first card that was dealt is no longer in this around. It's no longer visible or whatever, able to be dealt because it's already out. So there is an influence about what's going to happen next, right? This is a dependent probability. So we're going to solve it. These are dependent events, and therefore we're going to calculate the conditional probability. So the conditional probability says, hey, find the probability of getting a heart. That's 13 out of 52. Now, let's talk about this conditional probability. Because, oops, let me put this a little bit more full screen. All right. So because we selected a card, I don't know if it was hearts or not, but it doesn't matter. But we want a diamond. We're going to assume that a heart happened. Well, if a heart happened, that now means there are 51 cards left in the deck, but still 13 of them are diamonds. And that's what's considered conditional probability. So I want to emphasize that before letting this video go any further. All right, so what I've done there was, just to reemphasize it, there was 52 cards. 13 originally were diamonds, 13 were hearts, 13 were spades, and whatever and whatever. One's dealt. What's that probability? 13 out of 52. I wrote that in black. Should be good with that. Now we want to get a diamond. Well, first of all, how many outcomes are there available? It's not 52 cards anymore. There's 51. Okay, so that's why the denominator of 51 is written in red. One card's gone. Now, how come the numerator is still 13? Well, we're talking about diamonds, and if we assumed a heart was drawn, there's still 13 diamonds in those 51 cards, so 13 out of 51. That's all conditional probability is. Keep it simple in this course, right? From here, now we just multiply, simplify, and we get a total answer of 13 out of 201, which I was kind of curious myself, how likely is that to happen? It is about 6%, not 0.06%. I made a mistake there. So excuse that typo. 0.06, which is about 6%. Right. Wonderful.